Whoa.
Nothing. Okay. All right, so we've been looking at some integration rules. We came up with a kind of reverse power rule, a way of undoing our power rule for derivatives. And we also came up with a way of undoing our 6 trig functions. We discussed the idea that we can integrate term by term across addition and subtraction, the same way we can differentiate term by term across addition and subtraction. We can also pull a constant multiple out, integrate, and then multiply that constant back in the same way we do with differentiation. But one of the other things that we have talked about is the fact that we can't just multiply the antiderivative of 2 functions together for the same reason that we can't multiply the derivative of 2 functions together. We'd have to apply the power rule. Same with division. Just like with differentiation, we have a quotient rule. We have to come up with some way of taking the antiderivative of a quotient or even like a chain rule. And so that's what we're going to start to look at today. What happens if we have like multiplication or division, or if we have a composite function, a function inside of another function? What do we do in those situations to come up with a way of working backwards to undo those product, quotient, and chain rules? And one of the methods that we have for doing that is called U-Substitution. This is not going to work for every product. It's not going to work for every quotient, every composite function, but it does work for a lot of them. And the idea is that instead of looking at taking the antiderivative with respect to x, we let u be some function of x, and we take the antiderivative with respect to u. So here's what that looks like. Let's say that we want to take the antiderivative of x squared plus 1 to the 5th plus 2x with respect to x. Now, last week, the only thing that we could have done here would have been to try to expand that into one big polynomial and taken the antiderivative term by term. And if that had been a squared, that wouldn't be such a big deal. But I don't want to sit here and multiply x squared plus 1 times itself 5 times and then distributing that to x. So instead, what we're going to do is we're going to look for some piece that could be a function of x. And the other piece is going to be the derivative of that function with respect to x. So for example, notice that I have this x squared plus 1 to the 5th. I'm going to let u be x squared plus 1. So then what I have is u to the 5th, the stuff to the 5th, the same way we would do chain rule. So then what would happen if I took the derivative of this with respect to x? Well, I'd have the derivative of u with respect to x, also known as du dx, is equal to 2x. And we learned in the last semester that we can take these differentials du and dx, we can separate them. So if I multiply both sides by dx, I have that du is equal to 2x dx, which means that here this x squared plus 1 is u, and this 2x times dx is du. So I can take this antiderivative. You okay? Okay, so I can rewrite this as u to the 5th times du. How would I take the antiderivative of u to the 5th with respect to u? And I remember a. So we add 1 to the exponent, divide by that same exponent, and don't forget the plus c. Now, last week when we were writing our antiderivative rules, I don't know if it was this class or if it was 5th period, but somebody was like, why do we use u instead of x? And I said, well, it doesn't necessarily just have to be x. It could be any function of x. This is why I wrote those rules that way. How would you have done that, though? If you didn't recognize that this was the derivative of this and rewritten it this way, how would you have taken that antiderivative, right? So now what we can do is we can take that and change it back to our function of x. U is x squared plus 1. So I have x squared plus 1 to the 6th divided by 6 plus c. The du came out whenever I took the antiderivative. The du dx is gone because I took the antiderivative. And how could I check this? And to take the derivative of it, I'd have to apply. To take the derivative of this, I'd have to use, no, not quotient rule. I'd treat that as a constant 1/6. Chain rule. And when I took the derivative of the stuff, x squared plus 1, that's where I'd get my 2x that I started with in my antiderivative. We just undid the chain rule. We unchained the chain rule, right? Any questions about that? So the trick with U-substitution, the hard part's not going to be taking the antiderivative, because once you rewrite it correctly, we're just applying those same 7 antiderivative rules that we were before. The hard part of U-substitution is figuring out what u and du should be. And that part sometimes is going to take a little bit of effort. You might have to guess and check. Maybe you think u is this piece. Okay, well, let's try it and see what happens. Okay, that doesn't work. All right, let's try this piece as u and take the derivative and see what happens. Okay, that didn't work, and so on until you find something that did. So do you guys remember, like, back in Algebra 1 when you were learning to factor?
Yes.
And most of you didn't have a gimmick. Most of you, when you were learning to factor, you tried one thing. You tried 2 numbers. And then you switched them around, or you changed the sign. And if those didn't work, you tried 2 more numbers, and then you switched them around. And then you tried 2 more numbers, and you switched them around until you found the right combination. You guys remember doing that? And in the beginning, you were like, oh, this takes forever. But now whenever you factor, usually you're able to look at it and kind of play with it in your head a little bit. And you're like, okay, these are the 2 numbers and the way I'm going to do it. And you don't have to spend nearly as much time. Am I right? Some of you maybe. Some of you maybe not. Yeah, that'll get you far in life, copying. But my point is that U-substitution is going to kind of feel the same way in the beginning. You're going to try something and it doesn't work. And you're going to try something else and it doesn't work. And you're going to try something else and it doesn't work. And you're going to get frustrated. And you're going to try a 4th thing and you're going to be like, oh, thank God, I finally got it. But the more you do these problems, the easier it is going to be to figure out what you should be in the situation and make it work. So you don't have to try 5 different things. You go, oh, hey, I kind of remember something like this before. And when I did this before, this is what I did. So this is what I'm going to try first, is what I'm saying. Which is why we're going to spend a lot of time this week practicing, because the more you practice these, the better you're going to get at it. All right, so any questions about the first one? All right, so let's say that we're taking the antiderivative of x squared times 2x cubed plus 5 to the 4th with respect to x. Again, expanding this out is not something that I want to do. So I'm going to try U-substitution. Okay, do you guys want to try that? So let u be the 2x cubed plus 5. So the stuff inside the parentheses. So then du dx would be 6x squared. So then du equals 6x squared dx. So then if we look at this, we have u right here, except what do you notice is missing? I have an x squared, and I have the dx. I don't have the 6. I can't just put a 6 in there. If there was a 6 in there, I could pop it in the front. This 6 right here. I've got the x squared, and I've got the dx, but I have this extra 6. If we multiply by 6, we could put a 6 in there if we also divide it by 6. That's one way of thinking about it. Another way of thinking about it is this. If du is 6x squared dx, and I need x squared dx, then what if I multiplied both sides by 1/6? So then what we would have is that 1/6 du is equal to x squared dx, because those would cancel, right? So x squared plus dx isn't du, but it is 1/6 du. And now we have a constant that we can pop in the front. So what we have is the antiderivative of u to the 4th times 1/6 du. And because this is a constant multiple, we can move it to the front, like you guys said. No, we don't want to substitute u yet. We want to take the antiderivative now. So the antiderivative of u to the 4th with respect to u will be u to the 5th divided by 5 plus c. And now that we've taken the antiderivative of u with respect to u, we can go back and substitute in our function of x. U is 2x cubed plus 5. So we have 2x cubed plus 5 to the 5th over 6 times 5, 30, plus c. All right, any questions about that one? Okay, let's try another one. Antiderivative of x dx divided by the square root of 3x squared plus 4. Now, don't let this part bother you. That's the same thing. We're popping it at the end. I'm going to go ahead and rewrite this denominator as 3x squared plus 4 to the 1/2 dx. Or you can leave it in the numerator, however you want to do it. Now, again, I can't rewrite this to make it fit my basic antiderivative rules, and I don't have a division rule, a quotient rule for antiderivatives. So at this point, I'm thinking I'm probably going to have to do U-substitution. What do you guys think we should let U equal? 3x squared plus 4. All right, let's try it and see. So then the derivative of u with respect to x would be 6x. So then du would be 6x dx. Well, I've got the x dx. I also have an extra 6 that I don't need. Okay. So then 1/6 du equals x dx. So this x dx is actually 1/6 du, and this 3x squared plus 4 is u. And now we can rewrite our antiderivative as, instead of u to the 1/2 in the denominator, how about we go ahead and write it as u to the negative 1/2 and bring it up, times 1/6 du not yet. We could pull the 1/6 out. All right, see if you can take it from there.